Hi grade 10s, it's Gail again with video 2 on trig functions and sketch graphs. This time we're looking at the function y is equal to acosbx. During your trig investigations, you realized that the sine and cos functions are almost exactly the same. In fact, the only difference is that they wave up and down at different places along the x-axis. So if I take the sine function and I shift it 90 degrees to the left, it will be a cos function. It will be on top of the blue graph. And if I take the cos function and move it 90 degrees to the right, it will be a sine function. It will be on top of the red graph. So quite clearly, these two functions are very closely related. We're going to use this when we go through the function y is equal to acosbx. As a mathematician, you shouldn't want to learn too much replicated information. You need to save all your headspace for solving problems in maths and not crowd it with too much learning. On this whiteboard note here, I've drawn the functions y equal to sine x and y equal to cos x next to each other. The basic sine x function and the basic cos x function. So sine x starts at the origin, 90 degrees later it's at a turning point, down to a root, down to a turning point, and back to a root. The cos x function starts on the y-axis equal to 1, so it doesn't start at the origin, but then it follows the same pattern. So if we look at our 5-point plan, the shape of the sine x graph, I've copied that. Then the shape of the cos x graph, well, that is just the sine x graph shifted 90 degrees to the left. So I've taken this graph and just shifted it across 90 degrees to the left. So their shapes are different, just in terms of where on the wave it starts. The amplitude is the same, the period is the same, there's significant points at the same interval. And then obviously, because the cos x graph is actually very similar to the sine x graph, just waving at a different time. This time the graph doesn't go through the origin, but at 0 degrees, the cos of x is 1. So it starts up on the y-intercept over there. So the only differences that you need to worry about over here are the shape. And the only aspect of the shape is the y-intercept. It goes through the origin with the sine x function, and it starts at y equal to 1 on the cos function. And then obviously that corresponds with what happens at the origin. So we don't have to do all our learning again. On the next page, I've got a summary of the basic y equal to cos x graph, and then I'm going to jump straight into the general y equal to a cos bx function. You need to draw a sketch graph of the function y is equal to 0,7 cos x for the interval 0 to 360 degrees. So let's go through those 5 points. If you bear in mind the general function y is equal to a cos bx, in this case b is 1 and a is 0,7. And you know that this will be the amplitude, and 360 degrees divided by 1 equals your period. So it's a standard cos period. So let's fill in our 5-point plan. This is going to have the shape of a cos graph. The amplitude is going to be 0,7. The period is 360 degrees. Significant points every 90 degrees. And when x is equal to 0 degrees, so you substitute a 0 into your function in the place of x, you will get 0 degrees and 0,7. So notice it's not 1 like the standard cos function. It corresponds with the amplitude up here. So let's plot those points. We're going to start at 0.7, which is roughly there. 90 degrees further, we're going down. We're copying the shape over here. At 180 degrees, it's going to be minus 0,7. At 270 degrees, back to 0, and then back up to 0,7. So if you draw that graph, the same shape as the sine graph, there we have it. Okay, that wasn't brilliant. Fill in the coordinates of your turning point. So it's 180 degrees and minus 0,7, 360 degrees and 0,7. And this y-intercept here is also a turning point. So you're going to fill in its coordinates, 0 degrees and 0,7. Label your graph. Y is equal to 0,7 cos x, and you're done. The next function that we're going to look at is y is equal to minus 2 cos x. Over the interval, x is an element of 0 to 360 degrees. So once again, here's our 5-point plan. Shape, amplitude, period, the significant points, and what happens when x is equal to 0. The shape of the graph is a cos graph, but as you know from your investigation of y is equal to acosbx, if a is negative, then that has the effect of reflecting the graph about the x-axis. So I'm going to reflect that in my shape here. That is going to be the shape, the reflected cos graph. The amplitude is going to be 2, because the amplitude is the positive of A. A is negative 2, so the amplitude is 2. The period is going to be 360 degrees. It's as the standard cos graph because B is 1. So the period is 360 degrees. Once again, because the period's 360, the significant points will be every 90 degrees, like the standard cos graph. At x equal to 0, so if you type into your calculator negative 2 times by the cos of 0, you will get negative 2. So when x is equal to 0, y is equal to negative 2. We're going to translate that information onto the axes that I've drawn here. So at x equal to 0, y is equal to negative 2. I move 90 degrees on, and following my shape, I know that a root comes up next. Another 90 degrees is the next turning point. Another 90 degrees, the next root, and then the next turning point. And then you draw your graph, mark your turning points, and you're done. So this is 0 degrees and negative 2, 180 degrees and 2, and 360 degrees and negative 2. And of course, don't forget to label. Y is equal to negative 2 cos x. Let's just summarize that. You have a reflected cos graph with an amplitude of 2 and a period of 360. Now we need a sketch graph of y is equal to the cos of 3 over 2x from 0 to 360 degrees. Let's write down the general function y is equal to a cos bx. Let's match that up with our function that we've got. So a is 1, which tells us that our amplitude is the same as the standard graph, and b is 3 over 2, which tells us that our period is going to change. There's no reflection in this case. So the shape is the standard cos function shape. The amplitude is 1. The period is going to be 360 degrees, the period of the basic cos graph, divided by 3 over 2. Remember, it's divided by the absolute value of A. And so now you know that is 360 degrees. You're not going to get this wrong. Times by 2/3, and you get an answer of 240 degrees. So you've got a period of 240 degrees. The significant points will occur at every 90 degrees divided by 3 over 2, which is 90 degrees times by 2/3, and that will give me 60 degrees. And then on your calculator at x equal to 0, you will find that cos of 3 over 2x is 1. Because my significant points are every 60 degrees, I'm going to set up my x-axis to correspond with that. I'm going to mark every 60 degrees. So it's 60 degrees, 120 degrees, 180 degrees, 240 degrees, 300 degrees, and 360 degrees. The amplitude is 1, so I only need 1 and -1 on the y-axis. Label the axes. And then it's time to plot the points. At 0 degrees, the y value is 1. Then 60 degrees further on, we are following the shape. We go to a root. 60 degrees further on, we go down here to a turning point, a root, a turning point, a root, a turning point. And there we have it. What I want you to notice is that we fit in 1.5 periods. 3 over 2 is 1.5 periods in the 360 of a basic cos graph. So just to be fussy, let's go and do the turning points. This is a turning point 0 degrees and 1. This is a turning point 120 degrees and -1. And 240 degrees and 1. Remember, I said you only need a 1 period of turning points, and then you must label your graph. So it's y is equal to the cos of 3 over 2x. Okay, that wasn't too bad. Okay, this graph is one that often catches people out. The function is y is equal to cos of -1/2x. In your investigation of y is equal to acosbx, you discovered that when b was negative, there wasn't any reflection, no reflection. And that's another difference between the sine function and the cos function. With the sine function, the negative b reflected the function, and it doesn't with the cos function. So we're going to go through our 5-point plan here. The shape, we're tempted to reflect it, but we know that we mustn't. So it's going to be like that. Then the next thing is the amplitude. And the value of A is equal to 1, and so the amplitude is 1. The period this time is 360 degrees, the normal cos function, and we're going to divide it by half, and I'm not going to spend time on that now. It's 720 degrees. Then the significant points. Are going to happen every 90 degrees. The basic cos graph divided by half is equal to 180 degrees. And lastly, what happens when x is equal to 0? Well, If you type into your calculator the cos of negative a half times 0, you will get 1. Plotting those points at 0 degrees, whoops, I didn't put my y-axis scale in, there it is, 1 and negative 1. So plotting those points, when x is 0 degrees, y is equal to 1, following the shape, I know that I only have significant points every 180 degrees. So this is 180 degrees, that's 360 degrees. So my next significant point is a root at 180 degrees, and my next significant point is a turning point at 360 degrees and negative 1. And so once again, we only have half of the wave in the 360 degrees, which we should have known from looking at that half x. We would only get half a wave in 360 degrees. And then being pedantic again, coordinates of turning points, 360 degrees and -1. And you've got to be pedantic in maths, by the way. 0 degrees and 1. Label your graph. Y is equal to the cos of negative 3 over 2x. And still being pedantic, I haven't labeled my axes yet, nor my origin. And there's your sketch curve. There's your whiteboard note on the general function y is equal to acosbx with a summary of how to work out your 5-point plan. And the next sketch graph that we'll be looking at is of the function y is equal to a tan bx.